So, material characterization is an important aspect of the overall design, right? So, the next slide deals with the fact, what is that? We all know that's just a very simple bridge deck that had corroded steel rebar. That's just one of the 1,000 examples we can give. As I told you, last year we had a major failure in the coastal lines of a, I forgot, 16-story, 18-story building. Like that, we have many. I'm sure you all have. You know the issues. I don't have to elaborate on that. This is what we believe. The steel guys are going to be very unhappy for saying this. We know the steel bars are very common. We also know that they have excellent mechanical properties that we have been talking about. So we keep saying we call it 60 KSI. That's about close to 400 MPa steel bar, and it is about 200 GPa type thing. So how does that compare with FRP rebar? I'm going to focus only and only on glass fiber based rebar, FRP bar. I'm not going to get into the carbon based rebar. The reason is very simple. Of course, it's expensive. But at the same time, the carbon-based FRP rebars are primarily used as pre-stressing strands, not so much as reinforcing bars. Torre produces some of them, and they try to promote it as a pre-stressing element. I didn't do anything work in that area hands-on, but one of my close friends did a bridge in Detroit area. Yes, it worked out, but overall it didn't take off at this point. 10 years from now, who knows? It might. I don't know that. But as of now, even the codes are shying away from using carbon-based FRP strands or solid bars for pre-stressing. So the way we suggested to overcome that is normally what the steel guys do, they use a very high density type concrete. There are very stringent, very stringent guidelines to pour concrete in the US on bridge decks. I'll give you 3 or 4 stringent conditions, then we'll move on. For example, they don't want you to pour concrete in the morning as opposed to having it late afternoon, so that the evaporation of moisture is minimal while it is having initial curing. You understand? All the terms are important. Initial curing. So that way you would reduce the crack density. And then they want to have a very high density type concrete with low water cement ratios. When we talk of low water cement, that's where your problem is. First of all, you don't have very good QA QC when making concrete of a high quality. What does that mean? It means 4 or 5 things, not one, 4 or 5 things. Number one, you don't have a proper control on the water cement ratio. When we build a bridge deck, the slump and the water cement ratios must be between 0.32 to 0.35. If they are not, when I was building the McKinleyville Bridge, then the slump was too high. Would you believe if I tell you 20 yards of concrete was dumped? So he has to bring a new concrete. So that's just one of the many. Second, vibrational issue. You cannot over vibrate it. You have to use a certain kind of a pin, certain kind of RPM, certain kind of time, like 20 seconds, certain kinds of spacing between this vibration and the next. So that is another stringent condition. Thirdly, as I was pointing out, we must have an absolute minimum concrete cover where you get into environmental type issues. Where you have a concrete slab under controlled environment like a building, it may not be quite as bad as it is when it is exposed out. No matter what the exposure is, but one has. So we have, all I'm saying is our controls, especially the outside concrete, are extraordinarily stringent. That's all I wanted to say. Now, you can tell me or contradict me if I'm making right statements when it comes to making concrete in India or not. I've seen some that I'm not sure people really understand the meaning of slump when they're making concrete. See, they look more at workability, ease of workability, rather than the long-term consequences of that. All right, but anyway, so FRP rebar appears to be an alternative to prevent corrosion. That is the idea. Different types of FRP rebars. I showed you some already, a couple of them anyway. Before I go into this whole thing, I want to point out a couple of things. That is, I'll repeat it over and over because it's so important. It should get into your. Now we are moving into the design issues, right? That's why I'll repeat a couple of things so that will stick in your brain. Germans built a concrete bridge. They thought they are doing a non-corrosive system with FRP bar. Wonderful. Objective was great. You know what happened? They pre-stressed the bar to a point they did not understand the meaning of creep rupture problem. You know what a creep rupture is? You don't know. Okay. As a designer, you must know what a creep rupture is. Does anyone have any idea what it is? Okay. Suppose a bar static strength is 100 units. You will see the next few slides, the strength of the bars in a minute. I'm just conveying a conceptual message. if a bar strength is 100 units at failure under static conditions, what does that mean? And I said under static condition, I'm testing a bar in a minute or 2 or 3, yes, right? Okay, even that is incorrect, meaning ASTM has a certain rate of loading to get you. If I load it very fast, I can cheat you by getting 120 units. If I load it slower, I'll get a lower value. Why am I getting a lower value? That is a creep. But that creep is a 5-minute creep or 10-minute delayed creep. So you may not find a whole lot of difference. Now, that same bar I tested under 60% of the load, 80% of the load, 40% of the load, like that, for a longer time, that 80% sustained, that's what we call a sustained load, failed, meaning instead of using 100 units, I used 80 units, it failed in 3 days, under 80 units. And that same bar at 60 units failed in 20 days. The same bar at 45 units, failed at 45 units in 3 months. That is called, why is that? Because the sustained load is creating an issue here. What is the issue? The longitudinal force transfer from the shell to the core is making the bar diminish in its ability to sustain the full loading over a period of time. Therefore, the definition of creep is always a time-dependent phenomenon. Always. That's it. You see what I'm saying? All right. So what happened to the German bread? They thought they can pre-stress it at 60% or whatever. Yes, they did. The bridge functioned well, but after 90 days, I forgot the number of days or months, failed. So they never wanted to go there again. That's in 84, 85, 1986, you know. So that is one thing we all need to be careful of. Okay, along those same lines, there is a creep threshold value for it. Means just like your endurance limit, there is a threshold value. Our US Military Engineering Handbook, MIL 17 we call it, tells that threshold value is about 35%. But we are not allowed to design at 35%. You know, I was designing a FRP rebar bridge, and I was trying to design for 20%. The general said, absolutely not. Design it at 10%. So all I'm saying is you need to be cognizant of the whole concept about creep rupture issue. That's my first message. So I'm going to give you these messages. When you deal with concrete, the second important message is the whole design is more or less empirical based. Not all of it, most of it. That is why concrete is also a composite, right? So all the composite guys I told you before the break, aerospace guys, they don't believe in this computational stuff. They use that as a guide. I'm not saying they totally disbelieve it, so don't misquote me. I didn't say that. But as our president said, we trust you, but we want to verify you as well. You know, we know you're not a liar, but we just want to make sure you are not. So that is the philosophy. So with that, we do have, I will show you the development of certain theoretical approaches, but at the same time, we reduce that into simpler forms so that a designer can do his or her design and move on in life. He or she is not interested in the research component of it, you see. Tell me what my equation is, I want to do and move on in life. That's why you have these empirical values created for you. So most of the concrete designs, even though you have reasonable theoretical approaches, primarily they depend upon some of these empirical issues. I said theoretical approaches that are reasonable, I said, right? So what's unreasonable about it? In any mechanics kind of a scenario, in any mechanics, I told you the advanced mechanics of material types, we have three things to satisfy. What are they? The stress versus strain. That's one issue. For the second issue, compatibility of deformations. What is the third issue? Equilibrium of forces. If I satisfy these three, it's like a black box. I put these three and juggle it, I'll get a differential equation, and then you solve it. That is all there is to it in a finite element approach. Whereas when it comes to concrete, we are not satisfying all three of them. Of course, we must satisfy equilibrium. You cannot escape that. Of course, the stress is proportional to strain, which is force deformation relationship. But we are completely violating the compatibility issue. Why? Before you know it, concrete cracks. There's no way in the world you can now talk about strain compatibility or a deformation compatibility. That's where we are violating. That's why I said concrete is a reasonable theoretical approach, but not a 100% mathematically definable, agreeable approach. So keep that in mind. Now, these are the different materials. We talked about it in the last day and a half. I don't have to go in there. Somebody was asking me about the hybrid bars. Somebody was asking me about the hollow core bars. We went through all these. Of course, human curiosity, we went through all that, so which is good. But primarily we are going to be focusing on glass, which has 3 or 4 different kinds of glasses. One of them is the E-glass, S-glass, AR glass. AR is alkali resistant, and finally basalt. So basalt is also a kind of a glass, right? So that is where we are going to focus. We are not going to get into aramid. Why not? 3, 4, 5 reasons. One is the cost. The second is it creeps excessively than we want. We talked about creep, resistance, right? The third is it absorbs a lot of moisture, especially when the bar is under tension. Why it absorbs more moisture? The molecules are going to be separating apart and provide more
space for the water.
Exactly. So you see, we think very simple. we don't want to overly complicate it. Yeah. In US military, we have a saying. This is known as a KISS principle, KISS. You know what that is? Keep it simple and stupid. So everybody can follow through these without all these super duper theories and what have you. You see? That is the critical, so you don't make a mistake. What's my goal? My goal is not solving a 10th order equation, but goal is to make sure my structure is not going to collapse. That is the goal for any design. So, we are going to restrict our attention to glass. Surface. Ribbed surface. You have seen that yesterday. And there are different kinds of ribs. That is a rib. You see that? Then you have sand coated surface. That is the sand coating. In between those spirals, you have wrapped and sand coating. That's what that is. A whole thing, I mean. Then you have the deformed bars. You know, all these are deformed bars, different kind of lugs. Yes. Then obviously you have a helical, you know, that type of thing. So these are the different, I think I told you yesterday already, I repeat myself, that is the ones with sand coating give you the best result. Why do we need a coating or a rib?
Bond connection.
Bond is the important part of it. So, by helical type thing, I already told you, you're reducing the bond effect. Why? Because there is some smoothness along those fibers. So that, you can see that the fiber thing does two things, reduces the bond and also acts as a stress riser. So if when I tested the purely sand coated bar, I don't know you remember or not, I told you yesterday I got about 2200, 2300 psi, whatever that translates to. Whereas when I put the ribs on it, it came down to 1600. Steel is about 2000, you know, in that range. You know, but admittedly, 1600 to 2200, it sounds like 25% difference, and it is, again, from a grand scheme of things as a designer, it may not be a whole lot. Okay, all right. Now, so then I also said a word or two about solid versus the hollow bar. The reason a hollow bar never went anywhere is because, as is, I have an issue with the shear. The hollow bar makes it that much worse.
Yes. So, what is the difference between sand coated wrap and sand coated?
The wrap here implies, oh, I'm sorry. Oops. Okay. The wrap here implies this. Yeah, the spiral. And that creates a higher stress concentration at that point. A sand-coated bar is a more uniform bar. The idea there is the uniformity of the sand coating and the contact area between the bar and the surrounding concrete is much higher. That's why you are getting a higher bond resistance.
So when the helical form is not giving higher strength,
it is not.
Yeah, still we are using in practice helical and
look,
sand coating.
You see, yeah, I know, that's true. We do that too. it is again, one can argue by saying that sand coating is a bond issue of the resin, which might break
Easily.
in a long haul. So we have a backup. That's the reasoning behind.
There is another type like tubing. You were telling about tubing, helically tubing, or it is like here we are using one fiber wrap. Here tubing on that too.
Yeah.
So is that have any effect on the strength or?
That's what we are finding, that as I just said, it is, we believe, first of all, the strength is lower. May not be much lower, I don't want to dramatize it, maybe 10% lower. But that is because at these locations, it is a stress riser due to stress concentration. Again, may not be a whole lot, maybe a stress concentration factor of 1.1 will give you a 10% reduction, right? Like that. So please don't take my words in any extreme sense. All we are saying is, yes, there is a stress riser, but it is nominal, 10%, 15%. See, when I keep talking about the stress concentration, I said on one hand, with near zero radius is infinity. Whereas if I have a round one, it's 1.8, 1.9. So everything is in between, you see. So keep those aspects in proper perspective before you interpret it. Okay. I am please.
Because of wrapping, the failure mode may change.
That's what it is. That's exactly what it is. The failure modes, that's what we're going to be concentrating in the whole design. What are the different failure modes? What is it that's manifesting these failure modes? These are the fundamental issues. Once you understand them, really there's nothing to it, you know. Yeah, absolutely. That's how we try to attack a problem on a fundamental basis with a critical thinking, never ever by memorizing it. You lost the game once you tend to memorize it, you see. I'll tell you a story. We built Empire State Building in 1932, but the design, that's a Great Depression period. We started designing in 1920. That's before I was born, by the way. Then they put, Depression time means there is not many jobs. They put a lot of these mathematicians to work to solve these equations, blah, 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 right? And they came up with some numbers. You know what? One of the most brilliant engineer solved the whole thing in a couple of days. How? He figured out where the inflection points are, and then you use this equilibrium equation. Hey, this sounds good. You know what a farmer does? I don't know how many of you come from a farming background. I do. You would spit in the air and find out in which direction the wind is blowing, right? That's exactly the level we need to bring engineering down. I'm not saying you should not cross-check it. I didn't say that. But all good designers have a backup. Does it make sense? I'm not very impressed if you're going to give me a final number with a 10th decimal point of accuracy. As a designer, it doesn't make any sense to me. So keeping that philosophy in mind, that's what so all our major design offices have 2 or 3 people like that, the way I described, in there. So all designs, after all these computer-based checks and balances, they go to them and they will just look at it and determine, hey, this seems reasonable, it doesn't seem reasonable, move on, you know. So keep that in mind, because you're all practicing engineers, so ultimately that's what counts. All right, bar size and the nominal diameter, both in the imperial units and the metric units we gave, we maintained this similar kind of notation as you all normally know about it. That's item number 1. We stopped at 10, means what? We do not produce bars beyond 1 1/4 inch diameter. That's the point with FRP. Again, one of the major difficulties maybe with FRP is we are not 100% sure how to scale up a product. Whether it is due to shear lag, that's a great example. By now, everybody knows, right, what a shear lag is? So it could be due to shear lag, or it could be due to inadequacy in curing, or it is a major worry about creating more voids, and whatever that might be. I can assure you, scaling up may not be as easy as it is in an isotropic material. That is why we restricted to this. Again, remember what I have been telling you whole morning, the concrete guys always want to test it before, whatever the theory you may have, that's wonderful. We trust it, but we want to verify it also. That's why. So you have those, and I don't have to say a whole lot about the size factors. So the rebars are produced in high volume, and I started the work on rebars personally, but I'm not the one who initiated the work. Let me make that crystal clear. But I was the one who brought some scientific understanding around it. But the two industry guys came to me, wanted me to characterize it, and they were producing. One is a German guy from San Antonio, Texas. The other is also from Texas. They were using it for flooring systems, especially in terms of hospitals and the MRI interferences due to magnetization of the steel. So that's how I started the work. Okay, my state Department of Transportation supported me. So my first composites work started in 1987. You know how I started? I went to a conference. My governor said, he came there too. Governor Rockefeller, I knew him somehow. He said, hey, Hota, why don't you work in this area? I just came back from Japan. Oh, they have this lightweight thing. So he threw that at me. Believe it or not, I'm not ashamed to tell you. When he said, they call it composite, I thought, oh, gee whiz, I can do the job. You know why I thought to myself I can do the job? I was thoroughly confused. When he said composite, I interpreted that as a structural composite action. I didn't interpret it as a material composites action, you see? So that's how ignorant I was. So I was able to go from there, and he told DOT to give me some money to do the job. I was innocent enough to take it and struggle with it. Anyway, so that's what the mass production has come into vogue. Each bar, as I told you this, I will show you some. has a distinct strength and durability properties. Why distinct strength? I'll repeat it over and over. Strength is dependent on 4 or 5 factors, right? Size factor is one. Type of material is another, like glass, carbon, or whatever, right? Curing resin factor is the third. Processing is the fourth. So all these factors have an effect on strength, and likewise, similarly, on the durability. Properties again depend on the resin and the fiber. And the fibers may be of different kinds, as we showed. Majority of rebars are used in infrastructure or e-glass. Why? That is most economical, most dependable glass. S-glass is there. I just want you to be aware of it. I want to highlight a couple of points under S-glass. Those are as follows. Number one, S-glass has modulus of about 14 million psi, whereas E-glass is 10.5 million psi. So it's about 30% higher, 35% higher with S-glass. S-glass has a failure stress of the strand about 600, 650 KSI, whereas E-glass is only 350 to 400 PSI, about 60% of it. So that gives you number 2 bar to number 10 bar. We did all that with pH variations, with sustained stress or the creep. I have that report, 300 odd pages, and then we use that for outside environment for 3-4 years. That is where we created these Arrhenius curves, and then ended up concluding in a bar in a concrete environment made of E-glass and vinyl ester in concrete with a cover. We concluded it's about 108 years. Directly exposed without a concrete cover, it's about 92 years. That's one of the Indian gentlemen did fantastic work on that. My book talks about it too. Rebar surface, we talked about it a little bit. So please look how the variation is in terms of the strength of GFRP bar made of E-glass. I said it is 75 to 175 KSI. That is, again, roughly speaking, 450 MPa, for example, to 1000 plus MPa. That is the strength. The longitudinal modulus varies from 4 to 7.5 MSI. That is the stiffness. Somebody was asking me, why do I have such variations? Do you know? It depends upon the fiber volume fraction.
Also, it depends on the process.
Some it does, but primarily the function is the fiber volume. The reason I'm going a little slow, I want to tell you something. We learned a little bit, not a whole lot, about finding modulus, right? This morning before the break. Okay. Let us say I'm talking about, for discussion purpose, 60% fiber volume fraction fiber, which means what? 40% resin volume fraction. 0.6, that is 60%, times the modulus of fiber, 10 or 10.5, right?
Yes.
That's about 6.2, 6, in that range. Plus 40%, that's 0.4, times its modulus, which is about 0.2 million, that's 0.4 times 0.2 is 0.08, let's say 0.1. So 6.3 is what you're getting for a 60%. I created rebars up to 70%, and we did get up to 7.123 in that range. So it is that simple. Is that very accurate? No, it's not very, very accurate, but that's as accurate as you need as a designer. You don't need a third decimal accuracy for a designer. You understand what I'm saying? That is the stiffness part of it. In my morning computations, I didn't say a word about strength determined. I only focused. I know why I focus. So much easier to talk about stiffness computation than a strength computation. The strength computations are far more difficult. There are umpteen number of theories. None of them predict within a range of 10-15 plus minus 10-15%. They do not. Whereas the stiffness computation that I talked about, the rule of mixture, if you remember, predicts within 5%. Do you understand?
Sir.
That is exactly why I started out with that rule of mixture theory. That's why I stopped talking about it once I got into my chapter 3, where I am talking about the laminate theories and what have you. So here we don't even have to worry about a laminate theory business when it comes to a rebar. Are you with me?
Sir. Yes. These are for E-glass.
Doesn't matter. Go to S-glass, for example. Say the 60%. What are you going to do? 0.6 times 14 MSI, 8.4, right? That's all. Whether it is E-glass or S-glass or AR glass or carbon for that matter, when it comes to the modulus or the stiffness, it is always as simple as, what is the stiffness of the composite? Volume of the fiber times the modulus plus volume of the matrix times the matrix mod. It's as simple as that. Of course, we are talking without, implying without speaking that the void percentage is about 1% or less. That's what our preference is. Sometimes it's not easy. You will never get a 1% void if you are going to hand layer. You will have a higher value. So we do not want to. You will never also get a 60-70%, as I told you earlier, with a hand layer. Therefore, that is out.
My question is, can we use two different types of glass for a single rebar, and that's how can we increase the modulus?
Sure, absolutely. Sure. Only thing you need to be careful is With glass, it does not matter if you call it a hybrid with E-glass and S-glass, it doesn't matter. But if you're talking about a hybrid with glass and carbon, it might matter, implying that if you're having an environment where you have a high thermal fluctuation, for example, or if you have an environment where you have pH variation, where you're going to encounter galvanic corrosion for carbon, then it does matter. So you need to be careful about some of these variations. You're with me?
Yes. So why is E-glass preferred over S-glass?
Huh?
Why is E-glass preferred over S-glass?
No, the manufacturing is slightly different, but both are glass. But the message is E-glass is about 10.4 million psi, S-glass is about 14 million psi.
Why is E-glass more used in infrastructure?
Cost. That is the issue. Cost. The S-glass, where you need strength, because it's 50-60% higher, you use S-glass. So, what did I say? I said computations of stiffness are much easier with a composite than the strength. So, that is my fundamental message.
So when it comes to the steel, the modulus in compression and tension more or less equal. But when it comes to the GFRP, so the modulus is different. So till 2022, the ACI 440 is not recommended the compression usage of GFRP, but in 22, so they have included that. Just to throw light on it.
I will be discussing that extensively, but standardizing a compression test is not easy with composites, unlike metals. Why? Because micro buckling of the fibers. Therefore, the ACI code of 2022 allows you to use composite rebar in compression with a 10% reduction in the modulus, number one. But you know what? I'll be discussing that extensively. The ACI 2022 clearly says, crystal clear, that do not take advantage of higher properties of composite while that composite is in compression zone. Remember that. At least they are allowing us to take composite in the compression zone as equivalent to that of concrete. In the past, I fought on this compression failure mode. After that, I moved away. Therefore, I didn't fight on that. I was not on the committee. If I were on the committee, I would have fought that too. I would have gotten it better than same as concrete type thing. But that's where it stands anyway. Are you with me?
Yes.
So, let's talk a little bit about tension, strength, tensile strength. You know, the easiest, again, as a designer, not as a pure theoretician, remember that. The easiest way to compute the failure strength is consider the failure strain as something like 15,000, 18,000, and simply multiply it with the modulus, you got an answer. You see what I mean?
Yes.
So, I mean, again, I'm giving you now as a designer, not as a theoretician. Do you understand what I said? You simply accept that the strain to failure, I made this statement, I'm going to repeat the statement. In composites, when it comes to the strength related issue, we always say the limit strain, we do not talk about limit stress. We don't. Why? Because the moduli are different in different directions. Okay. That said, we have seen composite rebar failing at 22,000, and you say you multiply it with 6, then what do you get? 132 KSI, right? So, as a designer, even if I assume a 20% less, 18,000, I'm still getting 104 KSI. So, that's good enough for you, because from a design point of view, we are not using the failure,
Ultimate failure.
we are not using that as an ultimate failure stress or strain. We are not. What are we using? We test 24 bars, take the average, and you subtract from that average the 3 times the standard deviation. So, if you produced a lousy bar, what happens? Standard deviation goes up. Typically, we like to see from civil infrastructure or military infrastructure point of view, no more than 8% of standard deviation, preferably 6%. So 6 times 3 is 18% to 24. Call it 20%, that's the range we like to see. But if I have more voids, I will have a standard deviation of 15% or something, multiplied with a 345%, suddenly the bar strength dropped down to half, which becomes an uneconomical issue. Now, this is what ACI recommends. That is average minus 3 sigma. Okay. There is a big debate right now whether to even accept that or not. The ASTM does not accept that. What ASTM says is the 80% confidence level of the 95th percentile value of the bar. So what does that mean? We do this 10 bars or 20 bars or whatever. So we do it at 6 or 5 different places. So my bar strength, say if I say 100 units to failure, 95% of the bar should be above or equal to 100 units. That is called 95th percentile. But that must happen 80% of the time looking at 6 or 8 different manufacturers. That is what the ASTM calls it as a design value, ultimate design value. So see the difference. Of course, I too prefer average minus 3 sigma. So much easier to convey the message. But there are other. See, another very important reason why they do that is the failure distributions are harmonic, binomial, or the Weibull distribution. In composites, they say they are Weibull distributions. not the normal distribution. That's what they say. And they have a reason to say, I think I found why it is becoming a viable distribution as opposed to a normal distribution. I don't want to get there, but the message. So if it is not a normal distribution, then the question of average minus 3 sigma may not be all that accurate. That is why ASTM has a slightly different different definition for it. Does it make sense? So you don't worry about it. They'll give you, a manufacturer will say, this is my design strength. We guarantee you. Means he or she has to worry about it. There are a couple of manufacturers here. You need to worry about it. So this is an iconic machine that did the tension test. Well, now you know when I say I started the work in 87 or whatever. Now we have much more sophisticated testing machines. So, but at any rate, the other, you see the bond test we did? That's where, so when I say certain thing, most of the time I'm talking about it based on my first-hand experience. I'm getting old, therefore I ask my graduate students or postdocs to do the test. That is the shear test. Isopescu test. So
we are going to show that.
Oh, good, very good. Yeah, please pay attention. Ask him a lot of questions. Don't hesitate.
This is for the single plate shear test.
We have a double ones too. Yeah, double shear, single shear, and what have you. Okay, remember, what did I say? Bending type shear, which is what is known as interlaminar shear, is about 20-22 KSI. Whereas the in-plane shear, meaning that like this, single shear, double shear type, that is only 4.55 KSI. Why? That is primarily dependent upon the resin. Whereas the bending type shear,
Resin plus fiber.
resin, primarily the fiber effect. Of course you have resin effect too, no doubt. If you look at your VQ over IT shear diagram, you can tell pretty much what I'm talking about. You see? The complementary shear is the one that's going to drive the magnitude of interlaminar shear. Okay, here. Somebody kept asking me about the coefficients of expansion or contraction. So you can see I identified concrete, steel, GFRP, CFRP, AFRP, aramid that is. So why did we say, we give you a range 3.5 to 5.6? Very simple. Fiber volume fraction. If I have a higher fiber volume fraction, I will have a lower coefficient and vice versa. Look at the transverse coefficient, fairly high, primarily dependent upon the resin. And carbon fibers, some fibers have a negative expansion, remember. Not all fibers, some are. That's why we put it at 0. At the lower bound, about 4 at the upper bound. Please also note this is per degree F, not per degree C, because you deal with Celsius. That's why. Look at AFRP. What is AFRP? Aramid, which is some kind of a polymer. It's negative zone. So when you keep talking about the hybrid type thing, now you know why you need to be careful about. In a benign environment, it's okay, but not okay when it is outside, exposed. One of the major difficulties, as you note, is that there is no ductile plateau like steel. There is a little bit after about 90-95% of the ultimate load, you do have a slight degree of ductility. Not much, I don't want very little, a small kink, you know, at the top. You know, a little bit of it. You do find it. I tested thousands of bars, therefore I know exactly. So you do have that. And at the same time, the slope is the modulus much lower than that of steel. So one of the advantages is, as I told you, what did I say? The failure strains are of the order of 15,000 microstrain, whereas that of steel at yield is 1600, 1433 to 1633 type thing. That's a big difference. The energy that it is going to absorb is higher. What is the energy? Stress times strain by 2, right?
Yes.
Much higher with FRPs than with steel. That is why the fatigue lives are higher. Anything else you want me to say there? I think that's about all I wanted to say. You can see the GFRP, the blue line, very low, whereas the CFRP, I don't know how many of you know, we now produce CFRPs that are about 4 times, maybe a little bit more, stiffer than steel. So if you say steel is about 200 GPa, in that range to 10, we're talking almost 1000 GPa for the carbon, So,
Special grade of fibers.
so these are very special grade fibers, and primarily we have 2 manufacturing procedures for carbon. The special grade fiber production, we call it a PAN fiber, polyacrylonitrile fiber, and this is the manufacturing is very intricate. I don't know a whole lot about it. Let me make that clear. I know the characterization end of it, not the manufacturing end of it. So this is what we got from a tension test. You see the middle photograph there? It shatters. When it fails, it literally shatters. One thing I want to caution you, whenever you're handling or your workers are handling, make sure that they wear gloves handling the glass composite, because there are certain things that would get into the skin. Nothing harmful, glass is the most inert, but it can be irritating. So here are the different, this gives you an idea. We did a lot of work in terms of the properties. People from Florida, Atlantic University did a lot of work. And of course, Nani did some work. And Ben Mokrane from Sherbrooke did a lot of work. And you can see clearly how the strength of the bar is reducing with the size of the bar. You got about 3/8 inch bar. I got about 256, whereas a 6-inch bar is 77. Number 6 bar, I mean. So that tells you the shear lag effect. Okay.